We are told that Jupiter orbits 5.2 astronomical units from the Sun, and we were asked to find how long does it take Jupiter to orbit the Sun once. So I drew a picture here. Here is the Sun at the center of the solar system with Jupiter in its orbit 5.2 AU from the Sun. And to address this question, we're going to use Kepler's third law. So Kepler's third law states p squared is equal to a cubed, where p is the amount of time it takes a planet to orbit the Sun, and a is the distance to the Sun. Now p must be written in years when we use this equation, and a must be in AU, astronomical units, when we work with this equation. If you are given P or A in something other than years or AU respectively, you must do a conversion, convert to years or convert to AU before proceeding. So what we're going to do is we are told the distance from Jupiter to the Sun is 5.2 AU. This is going to be my A. So I could plug that in and I could say P squared is equal to 5.2 cubed. Now, if I go to a calculator and enter 5.2 and I cube that number, I will get 140.6 in my calculator. Here I will have p squared. What we want, though, is p by itself. We want the amount of time it takes Jupiter to orbit the Sun. So to get rid of this square, I will have to take a square root of both sides. If I do something to the left-hand side, I have to do the same thing to the right-hand side. When I take the square root of p squared, I will have p all by itself. When I take the square root of 140.6, I get 11.86. So I find that the amount of time it takes Jupiter to orbit the Sun once is just under 12 years. In the next example problem, we are told that if it takes 29.5 years for Saturn to orbit the Sun, what is the average distance from Saturn to the Sun? As a general rule, not only for Kepler's third law problems, but any type of calculation in general with this course, it could be a very effective strategy to begin by drawing a picture of what's going on in this problem. So here I have the Sun at the center of the solar system. We have the orbit of Saturn, and I'm going to draw Saturn in right here. And we are told that it takes the planet Saturn 29.5 years to go around once, and we are asked, what is this average distance from the Sun to Saturn? Whenever we use Kepler's third law written in this form, P is always going to be the amount of time it takes to complete one orbit measured in years. So hypothetically, if you were given a problem and given the amount of time for an orbit in seconds or days, you would need to convert that time scale to years before proceeding. In this problem, we were given the number of years for Saturn to go around the Sun, so we're good. So I'm going to set P to be equal to 29.5 years. A in Kepler's third law, when written like this, is the average distance between that object and the Sun as measured in AU, where 1 AU is defined as the average distance from Earth to the Sun. So if you are, for some reason, asked to find the average distance from Saturn to the Sun in kilometers, we would first need to find the average distance from Saturn to the Sun in AU, and then take that number we get and convert it to kilometers or whatever else we're given. So in this problem, we're trying to find the average distance from Saturn to the Sun. If the problem does not ask for a specific unit, then you could just find the distance in AU and you're going to be good and you're done with the problem. So to begin, after I draw my picture, the next thing I'm going to do is I'm going to rewrite the equation. So I could write p squared is equal to a cubed. And now I'm going to plug in this 29.5 for the p squared term. So I have 29.5, I have to square that, is equal to a cubed. I will go to a calculator. When I plug in 29.5, I square it in my calculator, I get 870. And a cubed, I'm just going to leave how it is for the moment. Now, the answer to our problem is not 870 AU. What we are trying to find is A, but what we have is a cubed. So we need to get rid of this cube. In order to get rid of a cube, you could take a cubed root. So I could take the cubed root of both sides. When I take the cubed root of a cubed, the cubed root will get rid of the cubed term on the right-hand side, so I'm just left with a. On the left-hand side, I take the cubed root of 870, I put that in a calculator, and when I hit enter, I get 9.55. So the average distance from the Sun to Saturn is 9.55 AU, or a little bit more than 9.5 times the average distance from Earth to the Sun. Now, in this problem, before I go on and talk about why Kepler's third law is written in this form, derive where it comes from, I want to make a statement about the math of solving this step right here. So, what is a cube? What is a cube root? What do these terms mean? Let's first go back to something we use a little more often. Let's think about what does it mean to square something? What does it mean to take the square root of something? So if I say 4 squared, that really means 4 times 4. And 4 times 4, we know that is equal to 16. Now, if I want to get from 16 back to 4, I would square root it. So I could say the square root of 16 is equal to 4. The idea of cubing a number and taking a cube root is the exact same thing. So for example, I could say 3 cubed, that is really 3 times 3 times 3. Now I have a cube, so I'll have 3 terms when I multiply these guys together, and I get 27. If I take the cube root of 27, I will get 3 out as my answer. Mathematically, when you're actually working through a problem and trying to plug numbers into a calculator, calculators do have the square root sign, but they don't explicitly have the cube root sign, so we need to use something else for this. So what we do in a calculator is if I have a number like, say, 27, and I want to cubed root it, what I would do is I would take 27 and raise it to the 1/3 power. So I would take the number 27 and I would raise it to the 1/3 power. And when I hit enter on my calculator, that will give me my answer. Or in this case, if I raise 870 to the 1/3 power, I would get 9.55. In this course, it is important to me that you believe what I tell you, not just because I say so. I don't want you to take anything I say at my word. I want you to believe what I say because you believe this is the way the universe should work. You believe that these things sound very natural. So we claimed, for example, that Kepler's third law relates the amount of time it takes a planet to orbit the sun to the distance the planet is from the sun via the relationship p squared equals a cubed. But you might want to ask, why is this relationship correct? Why not something different like p equals a, or p squared equals a to the 4th power, or p equals square root a? Why is this the relationship between the amount of time it takes a planet to orbit the sun and the distance to the sun? To address this question, we're going to make a few assumptions. We'll make some definitions. We will then recall some equations from ESC 175 and a few other equations from Physics 121, and we will end up arriving at this result. Now, I'm going to tell you right now, if you were to stop the video and not watch this video at all, you will not miss anything that you will ever need to do on any homework or exam. In this course, I'm not here to stress you. You will not need to actually be able to reproduce what I'm about to derive on the board. But as I said, it is important to me that you believe what I say because you believe what I say makes sense. So I'm going to demonstrate a simplified proof of this relationship. So to do that, the first thing I'm going to do is I'm going to assume that the planet goes around the sun in a circular orbit. All 8 of the planets do actually orbit the sun in elliptical orbits, but a circular orbit is a special case of an elliptical orbit. And also, to a pretty good approximation, the planets do orbit in circular orbits. Not the best approximation, but it's an okay approximation. Secondly, I am going to call this planet planet number 1. I am intentionally being vague about which planet is planet number 1. Maybe it's the Earth, maybe it's Mercury or Neptune or something else. Also, in this equation, we call A the distance from a planet to the sun, but I don't want to use the symbol A for the distance from the planet to the sun. So I'm going to define R1 as the distance from the planet 1 to the sun. Eventually, at the end of this proof, we'll have p squared equals r cubed, and then we could go back and redefine the distance from a planet to the sun to be A. But for the majority of this proof, the symbol A is going to be reserved for a different type of quantity. Also, I will define P1 as the amount of time it takes planet 1 to orbit the sun once. M1 will be defined as the mass of planet 1, and capital M with a subscript S will be defined as the mass of the sun. To work through this proof, we will need to use some equations we talked about in ESC 175 and Physics 121, and we'll need to take a few other equations. So we will begin with Newton's second law, F equals ma. We will then have to apply Newton's law of gravity. The force of gravity between 2 objects is Newton's gravitational constant times the mass of one object times the mass of the other object divided by the distance between the objects squared. We will then have to reach out to the Physics 121 course, and there is an equation that relates the acceleration of an object that is moving in a circle to the speed of that object. That is, the acceleration of an object moving in a circle is equal to the speed of that object squared divided by the radius of the circle. And then the final equation we'll need to call on is an equation from math that relates the circumference or distance around a circle to the radius of the circle. And that is c is equal to 2 pi r. So in this equation, the first thing I'm going to do is I'm going to begin at Newton's second law. The force on an object is equal to the mass of the object times the object's acceleration. So let's suppose we are talking about object number 1, planet number 1. So the force on planet number 1 is equal to the mass of planet 1 times planet 1's acceleration. So I could write this as the force on planet 1, and I will now specifically write m1 times the acceleration of planet 1. Now we could ask, what is the force that is pulling on planet 1? Well, planet 1 orbits the sun. Planet 1 is bound to the sun by gravity. So the nature of this force is the force of gravity. And we said the force of gravity is Newton's gravitational constant times the product of the mass of the sun and the mass of planet 1 divided by the distance between the sun and planet 1 squared. So I could write the force of gravity as Newton's gravitational constant, the mass of the sun, the mass of planet 1 divided by the distance from planet 1 to the sun squared, divided by r1 squared. And then the right-hand side of this equation will just leave as it was for the moment. Now, in this equation, the next thing we're going to do is we are going to notice that we are assuming that planet 1 is moving in a circular orbit. So the acceleration of an object that moves in a circle is the speed of the object squared divided by the distance from that object to the center of the circle. And the distance from the planet to the center of the circle is the same thing as the distance of this planet to the sun. So I could replace this acceleration of planet 1 with as being equal to m1 times v squared the speed of planet 1 as it orbits the sun, divided by r1. And everything on the left-hand side I have here, I'm just going to recopy. So I have a g, mass of the sun, mass of planet 1, divided by r1 squared. What I am going to do next is I am going to think about this v. V is the speed that planet 1 is orbiting the sun. So let's think about what that means. What is speed? Speed is the distance you travel divided by the time you travel. So if I think of speed as being distance over time, well, if I begin here and I go around the sun once, the distance I traveled would be the circumference of a circle. So in this case, I could say the speed of planet 1 could be equal to the circumference of planet 1's orbit, because that is the distance that planet 1 traveled. So that would be 2 pi r1 divided by the amount of time it takes planet 1 to make one orbit. That amount of time we said is p1. And so if I say the speed is this, I could say then the speed of planet 1 squared will just be 2 pi r1 over p1 squared. And if I square this term, I then get that v squared would be, when I square everything, the 2 pi will become a 4 pi squared. R1 will square that, I get R1 squared, and P1 will become P1 squared. 2 became 4, pi became pi square, R1 became R1 square, P1 downstairs became P1 squared, all downstairs. So I'm going to take this relationship for v squared, and I'm going to plug it in right up here. So when I do that, I will have the left-hand side of this equation is still going to look the same, and I will have g times the mass of the sun times the mass of planet 1 over r1 squared is equal to the mass of planet 1. V squared is this entire term. This entire term needs to be upstairs. So I will have a 4 pi squared r1 squared divided by p1 squared. And then this r1 downstairs, I'm just going to write again over here. At this point, I have fractions nested within fractions, but all the physics we're doing is now done. I'm just going to rearrange these terms and cancel a few terms. So the first thing I'm going to do is I'm going to just try to get rid of the fractions. So for the moment, I'm going to leave the left-hand side alone, and I get g is equal to g times the mass of the sun, the mass of planet 1 over r1 squared, and then I will have the mass of planet 1, 4 pi square r1 squared will be upstairs, 4 pi square r1 squared upstairs, and now I have a p1 squared and an r1 downstairs. p1 squared r1 downstairs. Now what I'm going to do is I'm going to simplify this somewhat. So I notice I have an m1 and an m1 on both sides, so I could cancel these terms. And at this point, I will now cross multiply. So p1 squared times r1 will come to the left-hand side, r1 squared will come to the right-hand side. So p1 squared times r1 comes over here. I get p1 square r1 times Newton's gravitational constant times the mass of the sun. R1 squared will come over here, so I get 4 pi r1 squared times r1 squared will give me r1 to the fourth. Now I am going to go ahead and simplify this a little bit more. And when I do this, I could see, okay, we are beginning with P1 squared R1 times Newton's gravitational constant times the mass of the sun. Then I have a 4 pi and R1 to the fourth power. I have an R1 that could cancel with one R1 over here. So R1 could cancel with this term, and this term will become R1 to the third. So what I am left with then is P1 squared times Newton's gravitational constant times the mass of the sun is equal to 4 pi times R1 cubed. And what I'm going to do next is I am going to bring R1 cubed to the left-hand side. I'm going to bring G and mass of the sun to the right-hand side. So I then could write this as P1 squared over R1 cubed is equal to 4 pi over Newton's gravitational constant times the mass of the sun. And I am going to call this the final result of the first part of this proof. Now, let's think about what we did here. We began by assuming that here is the sun at the center of the solar system. Here is the orbit of planet number 1. Planet number 1 is a distance r1 from the sun. It travels with a certain speed, and at that speed, it takes p1 amount of time to orbit the sun. We ended up finding a relationship between the amount of time for orbit of planet 1 and the distance from planet 1 to the sun. What if I wanted to consider planet 2? So I will say here is the sun at the center of the solar system again. Here is a different planet that I am calling planet 2. Very similar to before, I could say the distance from the sun to planet 2 is given by R2. I could say P2 is equal to the time for planet 2 to orbit. And just like before, we could try to work out a relationship between the amount of time it takes planet 2 to orbit the sun and the distance from planet 2 to the sun. So let's look at what we did. Now we're going to talk about planet 2. Okay, so instead of talking about planet 1, I'm talking about planet 2. So I'm talking about the mass of planet 2. I'll change that subscript to a 2 because I'm now talking about planet 2. I still have the mass of the sun because the sun is still the object that is pulling on planet 2 with the sun's gravity. I now have the mass of planet 2 in Newton's law of gravity. Now the distance from the sun to planet 2 is R2 instead of R1. I'm still talking about the mass of planet 2. So here's the mass of planet 2. Here's the mass of planet 2. Here's the radius, the distance from planet 2 to the sun. When I talk about the speed at which planet 2 orbits the sun, I will have the circumference of this orbit be 2 pi R2, and the amount of time it takes planet 2 to orbit the sun is now P2. So I will have an R2 over here, a P2 over here, R2 over here, R2 over here, R2 is over here, sorry, M2 is over here and here, R2 is over here. Basically, if I want to find a relationship between the amount of time it takes a planet to orbit the sun and the distance from the planet to the sun, my entire derivation will be the exact same thing. I was intentionally ambiguous about which planet I'm talking about. I just call these planet 1 and planet 2. But every step along the way will be the exact same thing. So I could say there is a relationship between the amount of time it takes planet 1 to orbit the sun and the distance from planet 1 to the sun. I could write a very similar relationship between the amount of time it takes planet 2 to orbit the sun and the distance from planet 2 to the sun. And that is still going to end up being equal to 4 pi over Newton's gravitational constant times the mass of the sun. Now let's think about what we have said in this problem. There is a relationship between the amount of time of an orbit and the distance from the planet to the sun, and that specific relationship we said was equal to 4 pi times the gravitational constant times the mass of the sun. Throughout this problem, the mass of the sun never changes. The mass of the sun could be treated as essentially similar to a constant. And g, Newton's gravitational constant, is just a number. It is what it is. So if I want, I could recognize we have the same term on the right-hand side of both of these equations. So I could say P1 squared over R1 cubed equals P2 squared over R2 cubed. Now, I was intentionally ambiguous about what type of object I'm considering. Am I considering Earth or Neptune or Uranus or any other planet? Now let's be specific. Let's say object 1 is Earth. And let's say we are measuring distances in AUs and we are measuring the period of the orbit, the time for one orbit in years. So now let's assume object 1 is Earth. And let's also assume, let's measure distance in astronomical units, and let's measure time in years. Well, I could plug specific numbers into this equation. How many? I have P1 squared over R1 cubed equals P2 squared over R2 cubed. How many years does it take the Earth to go around the sun? 1 year. So in this equation on the left-hand side, I would have 1 for the time to go around the sun once, squared. What is the distance from the Earth to the sun in AU? 1 AU. So the distance from the Earth to the sun is 1 AU. I would have 1 cubed on the left-hand side. On the right-hand side, I'm talking about another planet, and I'm still intentionally being vague about which planet I'm talking about. So I'll just leave this as P2 squared over R2 cubed. At this point in this problem, let's draw what we have. Here is the sun at the center of the solar system. Here is the orbit of Earth going around the sun. And here is the orbit of this other planet I'm talking about. If you want, you could draw the orbit of this other planet to be inside the orbit of the Earth. None of our results would change. We said that Earth orbits the sun in 1 year. That's how we get the 1 squared up here. And Earth is an average distance of 1 AU from the sun. That's how we get the 1 cubed term down here. I am going to now revert back to our original definitions. So I am going to now say P is equal to the time for planet 2 to orbit the sun. And I am going to now say A is the distance from planet 2 to the sun in AU. A is the distance from planet 2 to the sun and that's measured in AU. And this time for the orbit is in years. We were using r for the distance because we wanted the symbol lowercase a to be acceleration, but we are now done with that. And because I have another planet and I'm comparing that other planet to Earth, I'm not going to worry about labeling planet 2, planet 1 anymore. So when I do that, this equation would just become p squared over a cubed. All that's left to do is to cross multiply these two terms. So p squared times 1 cubed will give me p squared, and a cubed times 1 will give me a cubed. So what I'm left with then is a cubed is equal to p squared. So as long as I am measuring a in astronomical units and p, the amount of time for a planet to orbit the sun in years, I can relate these two quantities by Kepler's third law.